Dans le monde entier, la plupart des bâtiments à plusieurs étages sont construits en béton armé. Il y en a donc plusieurs dizaines de millions et il y en aura encore beaucoup plus car dans les prochaines 40 années, le nombre de bâtiments est censé doubler. C'est donc très important de comprendre du point de vue de l'ingénierie structurale comment ces bâtiments vont résister aux forces horizontales telles que les forces du vent ou des actions sismiques, surtout celles de plus forte intensité. Pour résister aux forces horizontales telles que celles engendrées par le vent ou les actions sismiques, ces bâtiments s'appuient sur des murs qui s'élèvent selon toute l'auteur du bâtiment et qui peuvent avoir différentes géométries. Une géométrie très commune, c'est la géométrie en forme de U, telle que le mur derrière moi, où on installe facilement des cages d'ascenseur et cages des escaliers.
The torsional actions of a building subjected to an earthquake, that is the twisting of the structure, is inevitable. And the extent of these twists really depend on many factors, including the position of the core walls away from the center of mass. The rotation of the wall can actually lead to significant damage, and despite all this, there has been a very limited amount of research on this topic.
This experimental research program here in the Laboratoire d'essais mécaniques, structures et génie civil at UC Louvain focuses on testing 3 half-scale reinforced concrete U-shaped walls. Each of these 3 tests differed by the way that we applied the loading. The first wall was subjected to a lateral loading. This is, it was pushed and pulled. The second wall was subjected to a twist around its vertical axis. And finally, the third wall that you can see here was subjected to a combination of push, pull and twist. This research was funded by an incentive grant for scientific research of the FNRS.
So for the 3 tests, we use a lot of instrumentation, including conventional instrumentation, such as LVDTs, potentiometers, micrometers, and also lasers. We also use 2 sets of 2 cameras to capture the 3-dimensional displacement field of the surfaces of the wall using digital image correlation techniques. Lastly, we also use high-definition distributed fiber optics, which are attached to some of the reinforcing steel embedded in the wall. And this gives us a really exciting opportunity to look at the strains, really high-resolution strains of the wall as it moves back and forth.
The data obtained from these tests will help researchers in the future to better simulate numerical models. More importantly, observations from these tests will help to develop recommendations for building codes and to construct safer buildings and promote more resilient communities.